Okay, so welcome to this next video in which we're discussing basic knowledge about the heart. Okay, so we've drawn this physiological picture, which is based on anatomical. I don't want to, it's a sort of rough anatomical picture, whereas now I'm going to draw a picture that's closer to the truth, that's more correct than this. This is very good for understanding the way the heart works, though, which is why I've called it a physiological picture. Right, okay, so we're now going to draw the actual anatomical picture so that we can understand the positions of the atria relative to one another. Okay, so let me do this slowly so that I get this right. Okay, so here is the right atrium, here, okay, like so. And then off the right atrium, you then have the right ventricle coming down here. Okay, and this comes up like so, right, to erupt out in a massive great blood vessel which we know is the pulmonary trunk. So here is the pulmonary trunk coming out there. Okay, then we also have on the left side of the heart here, coming around like so. So here's the left ventricle down here, and then right up here is going to be the left atrium, okay? So this portion here is going to be the left atrium. Okay, and I hope what this is sort of showing you is that it's more like a ball, where this left atrium here is very, very closely positioned with the right atrium, okay? And actually I would like to just sort of extend that round maybe a bit more like that, and maybe just extend this up going like that. That's probably slightly closer, so I'll have to add some colour in now to repair the damage that I've done. So here's the left atrium in red here, okay? What should we colour in the right atrium in? We'll colour it in blue over here. Okay, so this is the right atrium in blue. Okay, and then this big chamber here is the right ventricle coming off with the pulmonary trunk, and then the aorta sort of comes out from here. Okay, and it's a massive great blood vessel. And this here is the left ventricle, but the left ventricle kind of goes behind the right ventricle, and therefore it's coming out from behind it up there. Okay, and then what's going to happen is the aorta is going to come round in the aortic arch, like so, and the pulmonary trunk here is going to bifurcate into the two pulmonary arteries, okay, like so. And the right pulmonary artery will go behind the aortic arch, and the aortic arch will give off these massive three great blood vessels here and onwards like so. And that's gone awfully thin down there, but never mind. So this is a closer picture to the truth, and what I want you to gain from this picture is that the left atrium is this right atrium is in fact very, very close to the left atrium. Okay. Right, so now that we've got these pictures, let's in fact, I'll just label some things up on here that I haven't labelled on the other picture. So this is the right atrium here. Okay, and I should maybe put the vena cava, the superior vena cava in. So here's the superior vena cava, massive great blood vessel. Here's the inferior vena cava coming up here. Okay, and these things here, these are the pulmonary arteries now. So when the pulmonary trunk, this initial blood vessel to come out of the right ventricle, bifurcates into two, these two divisions of the pulmonary trunk, they are the pulmonary arteries. So this one that I'm specifically labelling here is the left pulmonary artery going to the left lung, and this is the right pulmonary artery which goes behind the aortic arch and will go into the right lung. Okay, and then the blood will go around the lung, get oxygenated, and then come back into the left atrium here through the four pulmonary veins, which I'm drawing here now. Okay, right. So let's now discuss the cardiac cycle then, and how this all works. So, in order to discuss the cardiac cycle, we need to discuss the pacemaker of the heart. So, what is it that makes the heart beat? Well, it is not external nerves. Unlike breathing, In the case of breathing, the phrenic nerve is continually making the diaphragm contract rhythmically. It's under the control of the brain. The heart is not. The heart will continue to beat if you cut every single nerve that supplies it. It is autorhythmic. It's capable of generating its own rhythm. Yes, nerves can change the activity of the heart, but they're not responsible fundamentally for its activity. Right. Instead, there is a certain portion of tissue up in the right atrium up here, or over here maybe. I'll show it on the anatomical diagram. It's somewhere around here on the anatomical diagram, up near where the superior vena cava joins the right atrium. And this portion is responsible for creating this pulse that the heart has. Okay, so this is the sinoatrial node, often abbreviated to SAN for short, sinoatrial node. And this is very, very important. Okay, right, so we begin then the cardiac cycle. The start of the cardiac cycle is that everything is relaxed. When the heart is completely relaxed, we say that the heart is in diastole, or cardiac diastole. So this just means relaxation of the heart. So currently it's in diastole, everything's relaxed. Blood is coming in from the superior and inferior vena cava, and it's filling up the right atrium, and also the tricuspid valves. They are currently open, basically, and blood is flowing from the right atrium into the right ventricle. So blood is coming in at the moment. Similarly, on the left side, the blood from the pulmonary veins is coming in and into the left atrium first, and then it's also going into the left ventricle. So blood at the moment is returning into the heart during diastole. Okay, at present, the semilunar valves here are closed so that blood cannot return from the aorta or the pulmonary trunk. And I want to stress that the way this happens is these valves, they're not under neural control, they're basically just one-way shunts. So they can be pushed by blood this way and open, but when blood tries to flow the opposite way, they just will not go. So how do I show this? Okay, right, so it's like a gate, basically. So here are these two gates. Let's say they're push gates, okay? And you can push them this way, so you can push them open, but when they get back to here, when they get to this closed conformation, and if someone comes from the other direction and tries to push them the opposite way, they just don't go that way because the gate's just not designed to go that way. So it's a one-way gate, basically. You can push the gates open, but only if you're going in one direction. So if the blood tries to push the gates open in the opposite direction, it just does not work, so the gates close, and instead the blood pushing on the gates in the opposite direction is just going to have the effect of closing the gates, and that's how these valves work. So they're effectively just one-way controllers, okay, or one-way gates. So these semilunar valves here on the aorta and the pulmonary trunk, they're these one-way gates which are stopping blood from flowing from the aorta back into the left ventricle and from the pulmonary trunk back into the right ventricle. Okay, so those systems are completely closed at the moment, whereas these ones are all open. Right, okay, then the first stage in the cardiac cycle is that the sinoatrial node, the SAN here, up in the right atrium, and I want to stress one thing, you only have one sinoatrial node. You do not have one in both atria. You have one in the right atrium, but you don't have another one in the left atrium. That confuses some people, and that's why I've stressed this importance of these two atria being next to each other. Okay, so the sinoatrial node is going to fire, and it fires roughly once every second. It's slightly more than that. Instead, the sinoatrial node usually beats around 70 beats per minute. BPM for short, beats per minute. Okay, so that's roughly the speed at which the heart beats when you are sitting down and at rest. So I'm at rest at the moment. My heart will be beating at around 70 beats per minute, I hope. Okay, right, so the sinoatrial node will fire off around 70 times per minute. So if we have a time here, time scale here, then in a second, we'll say it's roughly 1 beat per second. So if we put time, here's 0, here's 1 second, here's 2 seconds, here's 3 seconds, then it's roughly going to beat every second. It will be slightly less than a second, which is why I've drawn it here. So let's say it beats then, and it's then going to beat roughly about that time afterwards, and maybe here again, so it will continue beating at that sort of pace. Okay, now, so we were in diastole, and now we've suddenly hit one of these points, so the sinoatrial node is going to fire, and what does it cause? What does it mean for the sinoatrial node to fire? It means that it's going to start an action potential, basically. Now, the sinoatrial node, it is a piece of muscle tissue. Okay, this is what some people don't understand. It is a cardiomyocyte. The cells which make up the sinoatrial node are just cardiomyocytes. So they are cardiomyocytes. However, they are specialized cardiomyocytes. They generally are not contractile. Okay, so most of the cardiomyocytes in the heart are capable of contraction, but they are not capable of generating their own action potential. The sinoatrial node is a specialized portion of the cardiomyocytes, which isn't contractile, but is capable of generating its own action potential. So, we're going to see this as a running theme. There are two types of cardiomyocyte in the heart. There are the contractile ones, and there are the conductory ones. So there are the contractile heart muscle fibers, so contractile fibers we'll call them, and then there are conducting fibers. Okay, and the conducting fibers are generally not contractile, but instead they are involved in creating the autorhythmicity of the heart. And generally, all the conducting fibers are actually capable of generating their own action potentials, just like the sinoatrial node. And we'll see why they generally don't in the physiological heart later on. Okay, so the sinoatrial node then, it has generated its action potential. It's now firing action potentials out. And it's basically connected to all the other cells. Well, it will be connected to a bunch of cardiomyocytes around it, and it will cause them to all undergo action potentials, and then those cardiomyocytes will cause the next cardiomyocytes next to them to undergo action potentials. So basically, what you're going to get is this propagating action potentials, just propagating along this entire atria, so it will spread out from there, and all of the cardiomyocytes all over the place will be starting to undergo an action potential. And when they start to undergo an action potential, then they're going to contract. Now, basically, this initial spread of the action potential, it spreads across the right atrium and it spreads across the left atrium. But there is then something known as the atrioventricular septum, which I'll put here. Atrioventricular septum. So basically, there is a portion of connective tissue separating the atrial myocytes from the ventricular myocytes and stopping the action potentials in the atrial myocytes, causing action potentials in the ventricular myocytes. So basically, the spread of the action potential stops when it gets to this atrioventricular septum, as it's called. Okay, so you don't get the propagation of the action potential onto the ventricles yet. Okay, now that's going to cause the contraction of the two atria. And we'll continue this discussion in the next video.